Hello, welcome to another great video. For today's lesson, right, the main focus will be on the IUPAC naming of organic compounds. So we will do pretty much all the organic compounds that we have in grade 12 chemistry, organic chemistry, and that includes alkanes, alkenes, alkynes, all the way until ketones. All right, and then after all of this, we will have a few past paper examples. All right, so as part of the process when learning IUPAC naming, what we will include as examples are some of them will be past paper examples. All right, so stay tuned and let's start. So when it comes to organic compounds, one of the few things we need to understand is that nearly 90% of all compounds on Earth are actually organic compounds, right? This is due to the carbon's bonding properties, which we'll talk about shortly, right? So all organic compounds contain the carbon atom. That's another fact that you must also understand, right? And then there are, of course, of all those organic compounds, there are still compounds which will contain carbon, but they are not called organic compounds, or they are not organic compounds by nature. So these ones include your carbon dioxide, your carbonates, anything that has a carbonate, cyanide, and also carbon monoxide. So those ones are typically not organic compounds by nature, right? All right, so some other key things that we must understand or note about the carbon atom, right, is that, well, firstly, which is if we go to our periodic table, we find this carbon atom on our group 14, right? For that, it means it has a valency, or it has about 4 valence electrons, right? And for that reason, carbon is able to form about exactly 4 covalent bonds actually. And then another thing that we must remember is since all organic compounds contain carbon, well, most of them we will find that they also contain hydrogen. So what happens is most of them contain both carbon and hydrogen. So since carbon will always have 4 covalent bonds, and hydrogen will always have 1 covalent bond. It can either be to the carbon or to another atom, right? So that's one thing that we must note. And then carbon atoms can also covalently bond to other atoms except the hydrogen, even though mostly we will see it bonding to hydrogen, right? So all those other atoms, we usually call them heteroatoms, right? So these atoms will likely include nitrogen, sulfur, oxygen, and also some other halogens. The most commonly seen one in our grade 12 would be chlorine, bromine, iodine, and fluorine, right? So those are some key things that we must note about the carbon atom, especially in the context of organic compounds. The reason we're speaking about these is because, remember, we said all organic compounds contain the carbon atom, and because of this, 90% of all compounds on Earth are organic compounds due to the unique bonding properties of carbon. So we must then uncover what are these properties of carbon, which is what we just explained now. All right. So if you remember, if you try to draw the Lewis dot diagram of just a carbon atom, since it has 4 valence electrons, you'll have 4 dots surrounding the carbon atom, right? So this is what we mean by the valence electron, or by the 4 valence electrons, right? So these 4 means that carbon is able to form about 4 bonds, right? 4 covalent bonds. All right, so since we said most of these organic compounds will contain hydrogen, and then you'll find that hydrogen covalently bonded to the carbon atom, right? Since carbon is always present in these organic compounds. A great example of this would be, one of the examples actually would be methane. Let's say we take methane, right? And with methane, if you remember, it is by chemical formula CH4, right? So if you try to draw the Lewis dot diagram for methane, you'll find that you'll have the carbon, right, with its valence electrons. And then now remember, hydrogen will have one valence electron, which means it needs an extra one. So it will come here and bond and share with this hydrogen, with this oxygen atom. So the hydrogen comes and it shares with the carbon atom. Sorry, I don't know why I said oxygen. So now you start having 4 of these atoms that are sharing with the carbon atom to form methane, right? So they are all covalently bonded to one another, right, to complete their valence shells or their valence electron, using by virtue of the octet rule, because remember, it must have at least 8 electrons in its valence shell so that it can be stable. So with the exception of hydrogen, of course, it just needs 2. So now if you try to draw this using just the lines that we normally draw afterwards, you'll find that it's a structure that looks like this, because there are only one pair of electrons being shared for each carbon and hydrogen atom. You'll find that each carbon hydrogen bond that is in this methane molecule, you'll find that there's a single bond in between, because there's only one pair of electrons that is being shared, right? So this is an example of an organic compound that mainly contains hydrogen and carbon. All right, these two are the same things, just that one is showing you how the electrons are being shared, and then the other one is showing you the bond, which are these lines that you see here. These are the bonds. So these are all single bonds between the carbon atom and all the hydrogen atoms that are covalently bonded to it. Okay, all right, so let's continue. So one last thing I'd like to mention is that the carbon atom has the ability to actually covalently bond with other carbon atoms to form either a single, double, and a triple bond, right? So for instance, we will take just one example. You'll see more of these as we start naming our organic compounds when we get into it, right? So for instance, a great example would be ethine. There's an organic compound called ethine, right? So what happens there is you find this carbon being covalently bonded with another carbon atom, and then there are hydrogen atoms that are covalently bonded to the carbon atoms. So you find something like this. There's your carbon atom there, and then on the other hand, it is covalently bonded to our other hydrogen atoms. So when you draw it using just the dashes, like in this case, you'll find that it looks something like this. 1, 2, 3, because there are 3 pairs of electrons that are being shared between the 2 carbon atoms. Then there's this one there, then there's your hydrogen here, and the other hydrogen there. Remember, every time carbon has to form 4 covalent bonds, right? Nothing less than that and nothing more than that. Okay, so those are some few key things that we need to note about carbon, which are responsible for the reason why 90% of all compounds on Earth are actually organic compounds. All right, so there are also other factors, of course, or there are also other things that we would mention about carbon, but for now let's just focus on these 3. Okay, continue. Right, and then one more thing. So we call this a structural formula, right? of this particular organic compound. In this case, it's methane, right? It's called the structural formula. So after you get your Lewis dot diagram, of which we won't do for grade 12 and so on, we'll just go straight to the structural formula, right? We skip this part where you first get the Lewis dot diagram of that particular compound or molecule, in this case an organic compound or an organic molecule, but we'll just be doing structural formulae instead of the Lewis dot diagrams, right? This is another example of a structural formula. Okay, so we will define all of these terms a bit more later, more on this later. Okay, so now let's just do a few of the definitions that we would need. So one thing you must understand is that organic molecules, right, we usually represent them in a certain way, right? We can use a number of ways. It depends on the situation. It's either we use a general formula, right? That's when it belongs to a certain group of other organic compounds. Okay, we will define what we call such groups as well. Or we can use a molecular formula, or we can use a condensed structural formula, or we can just use a structural formula, which is this one. But basically the main idea is that we're trying to represent what it looks like, what that particular organic molecule would look like. All right, so right now we will define each of these, everything I just mentioned, and then also give some examples, all right, before we start with the actual IUPAC naming. So let's iron out the definitions, starting with the general formula. Of course, if you've already covered a bit of this content and you just need to know a bit more on the IUPAC naming, you can skip this part straight to where we start naming the organic molecules, your alkanes, alkenes, and so on, right? All right, so as I've already mentioned, general formula is basically just there to describe a homologous series of organic compounds. So we'll discuss more later on what a homologous series is, but essentially what it boils down to, it's just a group of organic compounds or molecules that usually can be described by a same formula. That formula, we call it a general formula. So homologous series and general formula, they basically define one another, right? So an example of a general formula will be something like C, which is for alkanes, right? For alkanes, we usually use the formula CnH2n plus 2. So what that means is, if for instance I'm looking for an alkane that has 2 carbon atoms, so C2, I will be able to know how many hydrogen atoms it has, because it will be 2n plus 2, which is 2 times these 2, right? That 2, and then plus 2. So what happens is all alkanes behave they follow this general formula. So if I'm looking for an alkane that has 3 carbon atoms, if I'm looking for an alkane that has 6, 7, and so on carbon atoms, I can always use this formula to know how many hydrogen atoms it will have, or vice versa. If it has 10 hydrogen atoms, how many carbon atoms will it have, and so on, right? So in this case, this would be ethane. So it would be CH2 plus 2 times 2 plus 2 is 6, right? So it's C2H6. Okay, so that's what happens with the general formula, right? So now we also talk about molecular formula. So you are more familiar with molecular formula because we've been using it since grade 10. In fact, this is a molecular formula, right? So we use the general formula to find the molecular formula in this example, right? So when we check the molecular formula of all organic compounds within the same homologous series or within the same group, right, we find that their molecular formula, they follow a certain general formula. if that makes sense. So which can be described in the case of alkanes using CnH2n plus 2. All right, so that's how it works. Okay, so molecular formula, as I've said, we've seen it quite a number of times from grade 10 until now. So you should be able to identify one when you see it. But in essence, we just use a molecular formula to indicate the type and also the number of atoms that are in a molecule, right? So it does not really tell us about the type of bond that is in that molecule, right? For instance, if I just give you this C2H6, right? Of course, you'd be able to tell this is an organic compound, right? But you wouldn't immediately know how many single bonds, double bonds, or triple bonds, if any, are available in this particular organic compound. Okay, so that's what we mean. Okay, all right, so molecular formula, we said this is for alkanes. So we will also talk about what alkanes are, alkenes are, and so on. Sorry, this is an error. C2 times 2 is 4. All right, it's fine. Plus 2 is 6. All right, yeah. So yes, molecular formula, we say essentially it tells us just the number of atoms and the type in a molecule. All right, so a great example, if we still use ethane, right? So ethane, we can say the molecular formula for ethane is C2H6, right? That's our molecular for ethane. So as we've already mentioned, that it tells us the number and type of atoms. We know that we have 6 hydrogen atoms. That's the number of hydrogen atoms. And then we have 2 carbon atoms. That's the number of carbon atoms. The type is we have carbon and hydrogen atoms. Okay, so that's what we mean by number and type, right? So we have 6. We have a total of 8 atoms, and then that's the number in total. And the type, we have both carbon and hydrogen atoms. All right, so that's another thing. And then we then also mentioned a condensed structural formula as another way of describing an organic compound, right? So now we're talking about a condensed structural formula, right? But it makes more sense to first look at a structural formula, because a condensed structural formula is like a summary of what a structural formula is. So a structural formula is, in essence, it shows us how atoms are attached to one another, right? It also shows us the type of bond or the type of bonds that are involved in that organic molecule in this case. So we use these lines. For instance, if you remember our structural formula here, we were able to show how these hydrogen atoms are attached to the carbon atom. At the same time, we were also able to show the type of bonds between the carbon and the hydrogen atoms. All right, so that's the main aim or purpose for a structural formula, right? So a single line here will represent that it means we had one shared electron pair, and it also means that it's a single bond. Double lines represent double bonds, triple lines, triple bonds. That's the last bond order that we have, triple bonds. All right, so that's how structural formula works. I'll also show you some examples. All right, so this is our description of what a structural formula is. As I've already mentioned, atoms will be indicated by the chemical symbols, while the bonds in between the atoms are indicated by lines between those atoms, right? And then one line would tell us that's a single bond, 2 lines, double bond, 3 lines, a triple bond, right? So some examples using the same ethane now. In the case of ethane, so we will have ethane, for instance, right? Ethane has 2 carbon atoms and then 6 hydrogen atoms. Okay, don't worry, we will delve into this deeper as we proceed. So if you check, these are all single bonds. These lines, there's one line between each hydrogen and a carbon atom, and there's also one line between the carbon atoms themselves. All right, these are all single bonds. So single bonds here. Right, and then now if we check, let's say now we have ethene. Ethene has a double bond, but let me show you how it looks like. There's a double bond between the carbon atoms. Right, the reason the H's are not vertically like in the case of ethane is because there's a concentration of electron pairs between these carbon atoms. And if you remember, the VSEPR theory says all these electrons will try to arrange themselves such that they are as far away from each other as possible, so that to ensure the stability of the molecule. That's why these hydrogen atoms are at an angle compared to when we are looking at ethane. So for ethane, they're like that. Just a side note. Okay, so now if you check here, now we have 2 bonds. This is a double bond, right? This one, and then these are single bonds. Right, these are all single bonds. So that's what we mean by lines telling us the type of bond. Double line, it's a double bond. 3 lines, it's a triple bond. So in the case of ethine now, it's another organic molecule. We'll have a triple bond there. So ethine, right? We'll learn more about these later, don't worry. For now, let's just focus on this example. Also, as we proceed, we will have to come back to these so that I show you how they apply later on. Okay, so if you think you don't get it now, don't worry, just hang on, it'll all make sense. So this is ethine, right? Notice that whatever happens, the carbon atom will always have a maximum of 4 bonds, nothing more, nothing less. Okay, if you start having 3 bonds but there's no other bonds outside of that, just know that you did something wrong. Okay, but we'll see that. So if you see, these are our single bonds, and this now is our triple bond. Okay, so that's what a structural formula looks like. So for me, it makes more sense to then now talk about the condensed structural formula after you've seen what a structural formula looks like. So the condensed structural formula, as I've already mentioned, it's basically just a summary of what a structural formula is. In fact, you could say it's more like a combination of a molecular formula and a structural formula. So the difference you will note when it comes to a condensed structural formula, we won't have this whole structure. We won't have all of this, right? But what we will have is something that looks like a molecular formula. But the difference there is, in a molecular formula, you do not show bonds, for instance. You do not show any branches that exist in the carbon chain and so on. But once you have a condensed structural formula, you can show all of those things. All right, so when I say branch in the carbon chain, I will elaborate as well, and actually you will see when we get to naming these alkanes, alkenes, and all these organic molecules what a branch looks like. Okay, for now, just know that there's something called a branch. Okay, so let us continue to define, or rather to give characteristics of a condensed structural formula. All right, so this is what we say about the condensed structural formula. It generally shows all the atoms in that molecule, while it indicates some or all chemical bonds. So what that means is usually single bonds are not shown or they are omitted, but you can also show them if you want. For example, so let's say example to this, e.g., if you have, let's say, ethane, right? The condensed structural formula, in fact, let's do this one. So what we want to do now is we will take all the structural formula examples that we have here and convert them into condensed structural formula. Let's start with ethane. Right? So what we will do is we will say this is our structural formula. Just our example here. So a condensed structural formula of this would be C. You basically go to the carbon atom, you write it down, and then you write how many hydrogen atoms are connected to that hydrogen, to that carbon atom. So this is our first carbon atom, which is this one, right? So how many hydrogen atoms are attached there? We find 3. Right, so we are done with the first part, or with the first carbon atom. We go to the second carbon atom, and then while we add it, we check between the second and the first carbon atom, what bond is there? Is it a single or a double bond? So since it's a single bond, we have the option of either indicating the single bond or omitting it. Let's first check what it would look like if we omitted it. So if we omitted it, we would just go to our second carbon atom. We write it again, and then we write how many hydrogen atoms are attached there. It's still 3. So this would be our condensed structural formula, right? And then when we want to show, I'll say or, if we want to show the chemical bond, which is the single bond between the carbon atoms, we would then say CH3. That's my first carbon atom and all its hydrogen atoms, right? Then now to my next carbon atom, what separates these 2 carbon atoms is a single bond. So you would draw a line like this, and you would write the other CH3 as well. So that's how we do a condensed structural formula, right? So we can say, I will label it structural formula and then condensed structural formula, like a table. All right, so what we're saying is we're taking the structural formula and then we are turning it into a condensed structural formula, because condensed structural formula literally comes from the structural formula. All right, so that's what we're saying. So what happens as well is you can also be given the condensed version, and then you have to translate it back to a structural formula, so it can go both ways. All right, so that's what it would look like. And then let's check if we have ethene now, how we would handle ethene. So ethene is a case where there's a double bond. So where there's a double bond, you also indicate it, right? So that one I would have to specifically state that you always have to indicate a double or a triple bond. It's not a matter of, you can't choose. It's not like when you just have a single bond where you have two options, either you include it or you don't. When there's a double bond or a triple bond, you have to show it, okay? All right, so in the case of ethene, you would say, first of all, remember we go to our carbon atom, the first one, we write it down. How many hydrogen atoms are attached to these carbon atoms? We have 2. Okay, we write H2. And then now, since there's a double bond between this first carbon atom and the next, we will indicate that double bond. And then we go to that next carbon atom, we write it down, we check how many hydrogen atoms are attached to it. 2. We write those down as well. So this is how the condensed structural formula would look like. And then again, we come to ethine, same story. How many? We write the first carbon atom, how many hydrogen atoms are attached to it? Just 1, so it's H. Remember, where atoms and subscripts are concerned, if the number is 1, you don't write it. Like in this case, I wouldn't write 1 here. I just leave it as it is. Okay, we know that there's a 1 there. All right, so now what separates this carbon atom and the next is a triple bond. So therefore, we would write our lines 1, 2, 3. And then our next carbon atom, we see that it's also attached to just 1 hydrogen atom. We write it CH. So that's it. That's how you would do a condensed structural formula. Then there's also one last condition when it comes to this condensed structural formula. So we can also show branches in an event that we have an organic molecule that has branches. We can show them in a condensed structural formula. We use brackets to show such. All right, so we will understand branches later, not now. But it's important that we lay all these rules now so that when we come back to them later, it connects. So whenever branches are present, we show them using brackets. So for now, I won't draw a structural formula for this particular example, but we can just consider an example where we have something like 3-methyl hexane. It's some organic compound as well. It's part of alkanes. So in this case, it has a branch in its third carbon compound, in its third carbon atom, right, along the chain. So how you would show this is, first of all, it's hexane, so it would mean that it has about 6 carbon atoms. And then so what this would look like is, we would say C, right? And then you'd have CH3, CH2, C, and then something like this, right? So if you're curious how the structural formula for 3-methyl hexane would look like is, let's take this. This is how the structural formula looks like. So we will learn later on about the long chains and the branches. So essentially what we have here is this long continuous carbon chain, right? This one. Now Now what happens is there is then now this external branch which is not part of the long chain. All right, so that's what we mean by branch. We have the long chain and then there's something outside of it. Okay, so this is how you show that branch. See, it is CH3 and it's exactly CH3 here as well. Okay, it's one carbon attached to 3 other atoms. All right, so but we will learn more about this in depth later on. All right, so let us continue. All right, so now another thing that we must mention is that there's a lot of these organic molecules. We have over 10 million or about 10 million, right, of these organic molecules. Now what happens is, just like periodic table of elements, where you have elements that behave a similar way being grouped in a certain group or being part of a certain family of elements, right? For example, if you go to your periodic table and you go to either group 1, there's group 1, 2, and then 13 to 18 there. For instance, if you go to group 17, you'll find what we call our halogens, right? If you go to group 18, you'll find noble gases, where noble gases, they have a full valence shell, about 8 electrons out there, right? And then in group 17, you have the halogens, they have 7 valence electrons. And then it's not only one element. For instance, in group 17, you have fluorine, chlorine, bromine, and iodine, right? So if you check, all of them will have the same number of valence electrons. So they have the same behavior when it comes to having these valence electrons, right? That's why they are grouped in the same group in that particular context, right? So what happens is, with organic compounds as well, we will do the same thing. We group them according to how they behave. So what happens is, there are organic compounds that have a similar behavior, and as a result of that, they also are grouped, right? So we usually talk about functional group and the general formula or homologous series, right? So that's how we group them. So when we group organic compounds, right? So we're grouping organic compounds, and then what happens is you get about two major ways of grouping them. And then one, you have your we'll call this one a functional group, functional grouping or functional group. And then secondly, you'll have a homologous series. Right? So now there's a specific way in which we define these. So a functional group, we would say it's a bond, right? Which could be a single bond, a double bond, or a triple bond. Or it's an atom, which can be any atom, carbon, especially in this case, because we're talking about organic compounds. We can be talking about carbon, hydrogen, and any other atoms that are involved, like halogens as well. Or it can be a group of atoms, okay? These then determine the physical and chemical properties of a certain group of organic compounds. So you'd find them in a certain group of organic compounds. And then if we see that this group of organic compounds typically has double bonds, or this group of organic compounds typically has only carbon and hydrogen, or this group of organic compounds typically has the carbon, hydrogen, and then a halogen atom, right? We would then group them into a functional group, right? So that's what a functional group is, and then we'll elaborate more later. For now, let's just write our definitions here. So we say functional group is a bond or an atom or a group of atoms, which then determine the physical and chemical properties of a group of organic compounds. Okay, so That's how we would define a functional group. It's a bond or an atom or a group of atoms which determine the physical and chemical properties of a certain group of organic compounds. All right, so then now we can also define a homologous series. So with a homologous series, it's just a group or a series of organic compounds that are defined, or that are described actually, by the same general formula. So what that means is, if you remember one of our examples here, we said a general formula, it characterizes a homologous series, right? So it's this formula here. It tells us how, if I go to that group of organic compounds, they will always, and all of them, follow a strict formula in how they form the compounds in general. So for instance, we made an example with alkanes, which we'll learn about very soon. Alkanes, if you go to all alkanes and you want to know how many hydrogen atoms an alkane that has 2 carbon atoms will have, you would then just plug it into this formula, and then you'll be able to sort of predict how many hydrogen atoms that alkane will have, because they all behave in this manner. They all follow this manner in how they form their bonds and how they form their molecules. Okay, so that's what we mean by general formula. So if they are described by the same general formula, that certain group of organic compounds will belong to the same homologous series. All right, so that's what we mean. So let's just put the definition here. All right, so that's our definition for homologous series. It's a series of organic compounds that can be described by the same general formula, or in which one member differs from the next with a CH2 group. So I'll show you what also that means. And then now, let's delve deeper now into functional groups and homologous series, and also the different types of these groupings in our organic compounds. All right. So we have this table right here. In this table, we will find pretty much everything we need when it comes to these functional groups and how to name them, and also how they are different from one another. Starting with alkanes. Alkanes, it's one group of organic compounds. And then we have alkenes, we have alkynes. We have about 9 groups: haloalkanes, alcohols, carboxylic acids, we have esters, we have aldehydes, and then we have ketones, right? So those are all the groups that we will be dealing with in organic chemistry. And then those are all the type or the groups of organic compounds we will be learning how to name, right? So let's start with alkanes. Alkanes, we have a general formula for alkanes, right? So the general formula for alkanes, this one, is CnH2 to N plus 2, right? And then the functional group, if you remember, we said a functional group, it can be either a bond, it can be an atom or a group of atoms, which determines the the chemical properties of physical and chemical properties of a group of organic compounds, right? So in this case, the functional group of alkanes, so every type of organic molecule that belongs under the homologous series alkanes. So the name of the homologous series is alkanes. Then the functional group is a single bond. So in this case, the functional group is a single bond. So all alkanes will have single bonds. That's what we're saying. So their functional group will just be single bonds, right? This is an example of what it would look like, of what a typical alkane would look like. And this one is named ethane, right? Which is another thing about alkanes. They have a specific suffix, which is the 3-letter word at the end of each of their names, and it ends with A and E, right? So you can have ethane, methane, propane, butane, and so on and so forth, right? They will all end with A and E. So these are suffixes, right, for the alkanes. So then we have alkenes. Alkenes, they have a different functional group and a different general formula. So the homologous series name is alkenes, right? Their functional group is just a double bond. So whenever you see a double bond, you know that's an alkene, right? If it's just a double bond and there are no extra things, it's the double bond and also only these H atoms, right? So here we have an example, which is ethene, and just like alkanes, these also have a specific suffix that they end with. So every name of this particular group of organic compounds will end with E and E at the end. All right, we will do examples of these and you'll see. And then we have alkynes, another homologous series. Alkynes have a general formula of CnH2n-2, right? So what happens there is all of them will have triple bonds in between their carbon atoms, right? So now these three, alkanes, alkenes, and alkynes, what happens is you won't find any other atoms in their structure except carbon and hydrogen. So they are, because of that, they have a certain name that we use for them. We call them hydrocarbons because they only have hydrogen and carbon in their structure, in their molecular structure. So these are called hydrocarbons, right? The name hydrocarbons, or what it means is, it's an organic molecule that only contains hydrogen and carbon in its molecular structure. So alkanes, alkenes, alkynes are what we would call hydrocarbons, right? So that's one thing we must know. So these homologous series, alkanes, alkenes, and alkynes, are called hydrocarbons because they only have carbon and hydrogen as part of their molecular structure. Nothing else. You won't find any other atom inside their structure. Now we continue to haloalkanes. Haloalkanes is another homologous series. Another name for them is alkyl halides, right? So what's different with these ones now is they have the halogen atom, which is Cl in this example, and then they have the structure that we used to, which is carbon and hydrogen atoms, right? So they are called haloalkanes. So basically it's an alkane that has a halogen atom attached to it. For instance, if you remember, we had ethane here, right? Ethane had only H atom, so we removed, or we substituted this one H atom with a halogen atom, right? And then now it changed entirely from being an alkane to being a haloalkane. The name haloalkane means there's a halogen plus an alkane there. So the process of substitution happened. That's why we changed from it being a complete alkane to it being a combination of a halogen and an alkane, right? Right, on our list next we have alcohols. Very interesting stuff. So now alcohols are actually organic compounds as well. So with alcohols, what happens is their homologous series is the name alcohols, and then this is their general formula. So all alcohols will have this general formula, and then now they have what we call a functional group as well. A functional group is the hydroxyl group, which is the OH atoms, right? So you'll find the carbon atom and it's attached to one OH atom, and then here you can then have, depending on the alcohol, you can then have your hydrogen atoms being attached here, right? So that's how you will see if an organic compound is an alcohol or not. It has to have one OH group, also called the hydroxyl group. This is the functional group of alcohols. And then on the other sides of the carbon atom, you might find the hydrogen atoms there. So, and then an OH group will be normally bounded to a saturated carbon atom. We'll talk about what saturated means, but basically it's when an organic compound only has a single bond. So we call them saturated. All right, so that's what happens here. And then ethanol is an example of an alcohol. So if you check, I'm sure you've seen this structure before. This is simply what we would call an alkane. And then in that alkane that we saw, it was ethane. So there was just hydrogen here. But now that hydrogen has been substituted by this OH group. So to make ethanol, okay? So this is an example of ethanol. And when it comes to suffixes, their names end with OL. So if you check ethanol, and then compared to ethane, right? Do you see? That's the difference. Compared to ethene as well, ethyne. So all of them will have a specific suffix. And I'll show you how we get the prefix now. Because they have, all organic compounds or molecules are made up of this suffix and a prefix, okay? But for now, let's focus on these. All right, same as here, we have chloroethane, right? Chloro is because now there was a halogen here. So the suffix, the prefix will be chloro for chlorine, and then ethane for the fact that it's an alkane, right? It has an alkane structure. Because remember, a haloalkane is basically an alkane that just has a halogen or halogen atoms in it. Now, we go to carboxylic acids. Now these ones, their general formula is CnH2nO2, right? Compared to the hydroxyl group, the carboxylic acids have a carboxyl group, right? So it's basically a carbonyl plus a hydroxyl group to make the carboxyl group. So you would see them with this COOOH, COOH. Right, so here's an example. Ethanoic acid, right? So their name will always end with anoic acid. That's your carboxylic acids there. And then, like I said, we will do examples of each and every one of these as we proceed with this video, okay? So stay tuned. So now we have esters. Esters, their functional group is this one, which is the carbonyl group, which is just COO. So one of the oxygen atoms has a double bond, just like here. But notice the difference. Here it's COOH, the carboxyl group, and the carbonyl group is COO only, COO. So the C has two oxygen atoms being attached to it, and then doesn't have any other atom being attached to it except another carbon atom, okay? So 3 of its bonds are taken up by these 2 oxygen atoms, and then the remaining one, it attaches to a carbon atom, right? If it's something like this, let's say here there was an H, then that would not be an ester, it would be something else, right? It has to be attached to a carbon atom here, right? Now, or if it was like here, we have an H, that also wouldn't be an ester, it would actually be a carboxylic acid, because if you check COOH, right? So we will discuss more as we proceed. And then these ones, they end with OAte, so like ethyl methanoate, right? And then that's how we name them. Then we have aldehydes. Aldehydes, their functional group is the formic group, which is COH, right? It's just a double bond between the C and the O. And then the carbon, where the double bond between the oxygen and the carbon is, that carbon will also be bonded to a hydrogen atom. Then here you can have carbon and so on. Or you can have just hydrogen. Right, so the formic group, it's their suffix, not formic group, sorry, the aldehydes, their suffix is anal. So ethanol is anal, ethanol is a great example of aldehydes. It's anal, anal, anal. So that's their suffix, okay? And then we have ketones. Ketones, carbonyl group, right? And then here, if you check, there's a difference now. Here, the carbon atom that is covalently bonded to the oxygen atom, that carbon atom should also be bonded to 2 other carbon atoms on each side, right? Unlike here, where the carbon atom that's covalently bonded to that oxygen atom is bonded to a hydrogen and can be bonded to anything else after, right? So here, the carbon atom must be bonded to other carbon atoms. Then we know that it is a ketone. So the homologous series here is ketone, and this is their general formula, and the name of their functional group is carbonyl group. So carbonyl group is their functional group. And then here is unknown. This one, don't mind this, it's this unknown. That's their suffix. So if you check here, it ends with unknown. It's propanone. Right, so that's one thing we have to understand about grouping these organic compounds, okay? So now we will start focusing on the homologous series alkanes. All right, we will check alkanes, how to name alkanes, and the different type of alkanes. Right, so remember, with said that with alkanes, okay, let's come here. Alkanes, alkenes, and alkynes, we said that these are what you would call hydrocarbons. So perhaps before we just go through alkanes, let me show you what we mean by that. So we said alkenes, alkynes, and alkanes are hydrocarbons. So hydrocarbons, they are also divided into 2. There's what you call aliphatic and aromatic hydrocarbons. All right, so what happens is, okay, we have aliphatic. So let's call these ones and they can also be aromatic. Aromatic means they have a certain type of smell. That's where you find your benzenes and so on, right? So number 2, they can be aromatic, right? So I'm not going to focus more on the aromatic ones, but I will focus more on the aliphatic ones. So with aliphatic, right, we get 2 different kinds here. We get that we can have 1 saturated hydrocarbons and also unsaturated hydrocarbons. That's 2 under aliphatic hydrocarbons. All right, so you have these ones and you have these ones, unsaturated and saturated. So saturated are those hydrocarbons that you will find them with single bonds only. They don't have anything except single bonds, right? We call them saturated hydrocarbons. And remember, here we're talking about alkanes, alkenes, and alkynes. So we said the saturated ones contain single bonds only. Right, between the carbon and any other atom. Right, so these ones, alkanes, belong here. Alkanes belong to this type of hydrocarbons. It's a type of hydrocarbons. And then when we go to saturated hydrocarbon or unsaturated, here we have multiple bonds, right? So we have at least a double bond or triple bonds. In fact, let's say double bonds and triple bonds. So this C atom will be bonded to other atoms via a triple or a double bond. So here we're talking about alkenes and alkynes. So if you check, there's a double bond here between the CC atoms, and there's a triple bond here between the CC atoms. So those are alkenes and alkynes respectively. Right, so that's what we mean by unsaturated. They basically have either one double or triple bond or more, right? But at least one. So here we're talking alkenes and alkynes. So when we say something is an unsaturated hydrocarbon, it means that it contains at least one double or triple bond. And when we say something is a saturated hydrocarbon, it means it contains only single bonds. Right, that's what it means. So that's one thing I wanted to mention before we go forward and then start discussing alkanes and go even deeper. Right, so that's one thing you must understand. And yeah, all right, so let's just add here the definition of hydrocarbons. So yes, these are organic compounds that only consist of hydrogen and carbon atoms. So it's in the name itself. So we have hydro for hydrogen and carbons for carbon atoms. All right, so if you check here, we have this hydro, and then we have carbons. Okay, so it's carbon and hydrogen. That's what we mean by hydrocarbons. Only carbon and hydrogen, nothing more, nothing less. All right, so now we can start talking about alkanes. Naming or learning how to do IUPAC naming for these organic compounds. So our first focus will be on alkanes, but before we actually start, let's just remind ourselves that alkanes typically have these four characteristics or traits, right? That includes the fact that they are hydrocarbons. In fact, they are saturated hydrocarbons because they have single carbon to hydrogen and carbon to carbon bonds, and also they have a general formula, which is that one of CN, H2N plus 2, and of course they have a suffix. If you remember our table here from our previous video, we said they use this suffix, or it was written name ends with, but that's just an explanation of what a suffix is. So their suffix is ANE, right? So that's one trait of, or that's one other characteristics of alkanes. Okay, so we must make sure we recall all of those, and then after we will just take the basics of IUPAC naming and how this system works and its nomenclature, right? So let's get to it. These are our characteristics of alkanes, okay, just to recall. And then remember, we said this N, it represents the number of carbon atoms. So which means that if you had, let's say, 10 carbon atoms, and you want to understand how many hydrogen atoms that specific alkane would have if it had 10 carbon atoms, you would simply plug it into this formula, and then you would find that, for instance, if you had 10 carbon atoms, you'd say, well, 2 times 10 plus 2. That means this alkane will have 10 carbon atoms, and 2 times 10 is 20 plus 2 is 22. So it will have 10 carbon atoms and 22 hydrogen atoms. So that's one thing about the general formula. And then their homologous series, it's alkanes. Okay, so now when it comes to the IUPAC naming system, it comprises of 3 things. It will have a start, or the start of the name, which is the first part, and then it will have the body or the middle part, and then it will have the end or the suffix, right? So those 3 things are called the prefix, which is the start of the name, the stem, which is the body, and then the suffix, which is the end of the name. So that's one thing. Let's put it here. All right, so these are the 3 things that make up an IUPAC name for any organic compound that we will deal with in this series. All right, so prefix, it describes, or usually it will tell us the functional group of that particular organic compound and where it's located across or along the carbon chain. Because remember, usually we look for a carbon chain, but we'll get to that, don't worry. And then the stem will tell us how many carbon atoms that particular this organic compound have. And then the suffix will also tell us the homologous series, right? So in the case of alkanes, our suffix would be this one, the ANE. All right, so we will get to how we use it for different hydrocarbons and for other organic compounds, how we use the IUPAC naming system. So now we're just introducing it. Like I said, it comprises of 3 things: the prefix, which is the start of the word, the stem, which is the body, and then the suffix, which is the end part, right? So that's what it is. In fact, let's rearrange this so that we can include what I just said, that is a body and so on. All right, so we're saying that the prefix would be our beginning of the word, right? And then it will tell us the functional group of that particular organic compound and the location of that functional group, or where it's found along the carbon chain. All right, and then the stem is what we would call the body in layman terms. So this is just the body. Right, and then the body will tell us the number of carbon atoms in that carbon chain, that continuous carbon chain. Usually we look for a continuous carbon chain. All right, so then next we focus on the suffix. The suffix, it typically tells us about the end part of the word. So that one will tell us about the homologous series of that particular organic compound that we would be trying to name. Okay, so in the case of alkanes, remember, we'll say the suffix will always be ANE. All right, or ANE. So I'll just call it the end, right? That's what it is. So now these things are what we would look for in order to name any organic compound: the prefix, the stem, and the body. So where we normally start is we look at the stem, because it is the one deciding factor after we've counted the number of carbon atoms in a continuous carbon chain for any organic compound, right? We would be able to then name that carbon chain, right, using the stem, and which is guided by how many atoms, how many carbon atoms are in that carbon chain. So we focus on organic compounds that have in their carbon chain at least 1 to 10 carbon atoms. Anything outside of 10, we don't really do it in grade 12 or grade 11. I'm sorry, only grade 12. There is no organic chemistry in grade 11. So we don't really do it in grade 12, right? So it gets a bit complex once you pass the 10th organic, the 10 mark for the number of carbon atoms, right? So what we do is we list all of them from 1 to 10, right? So we know that if an organic compound has 1 carbon atom, it will have a certain stem. If it has 2 carbon atoms, it will have a certain stem name. If it has 3 and so on, it will have a certain stem name, all the way up until number 10. So let's just put a table here so I can show you. Right, so now let's consider our table here. So how the stem names would look like is, for instance, if you have 1 carbon atom, that organic compound in its stem, it will have meth. Right, we put a dash because there will be something else that follows after. Remember, it's a stem, it's a middle part of the word, so the word is not really complete. And then if it has 2, it will be eth or eth. Let's say eth. If it has 3, it's prop. If it has 4, it's but. If it has 5, it's pent. Right? If it has 6, it's hex. 6 for hex. Hex for 6. If it has 7, it's hept for 7. If it has 8, that's our octopus. Right, if it has 9, it's our non. So you must know all of these, by the way. They won't give you in an exam or anything like that. You must know them off by heart. Otherwise, you won't be able to name these organic compounds when you get them in the exam. So how do you get to know them? It's easy. You just practice over and over and you'll get a hang of it. You don't look at it once and think you will know all of it. Well, you can, but I wouldn't count on that. So like I said, after the number of carbon atoms are above 10, we usually do a condensed structural formula because it becomes a repetitive thing, right? And we won't really focus on anything larger than 10 for grade 12, right? So this is what we will do for now, 1 to 10. So 1 meth, 2 eth, and so on until dec. Right, so DEC. Now, these are all the stem names that we will be using continuously when we do the IUPAC naming for all organic compounds considered here. All right. So it's not specific to alkanes only, but all other organic compounds. So now, when we look at alkanes, coming to alkanes now, let's start the IUPAC naming of alkanes. Now that we've introduced that basic, so our first focus will be on straight chain alkanes. So the reason I'm focusing firstly on these ones is because straight chain alkanes are quite simple in that they do not include a prefix, only the stem and the suffix. Right, so you will understand the reason for this once we do the branched alkanes or the ones that have alkyl groups. Right, so for straight chain alkanes, it's simple. Usually they will only consist of the stem or the stem name and also the suffix. So if the straight chain alkane has 1 carbon atom in its structural formula or in its molecular formula, it will be called meth, and then plus the suffix, which is ane, so it's called methane. Right, so I'll put a table here. Right, so if you check, we have methane, which is when that particular simple straight chain alkane has 1 carbon atom. We have ethane when it has 2 carbon atoms. We have propane, butane, and all the way up to decane or decane, right? So how that looks like is, like I said, for straight chain or simple alkanes, what we usually have is just the stem plus the suffix, and then we get the name of the alkane, or simple, let's call it a straight chain alkane name. They are usually called simple alkanes, right? So that's what typically happens. So as an example, we would take, say, e.g., if we check, let's take pentane. Pentane has 5 carbon atoms. You see here, number of carbon atoms, it's 5, this one, right? It has 5 carbon atoms, and therefore the stem, if you remember, we come here, we said any organic compound that has 5 carbon atoms in its straight chain, right, is called, in its continuous chain, is called pent. The stem name will be pent. So stem here would be pent, right? And then plus the suffix, since this is an alkane, right, the suffix will be ane. So when we add these together, we get pentane, right? So we do this for all these straight chain alkanes. However, it doesn't matter for methane, ethane, propane, and I think, yeah, methane, ethane, and propane. Though the first 3, they will always be just simple alkanes. There's no other way of naming those ones. And then, or also butane as well, yes. So that's how we typically name the straight chain alkanes. 1, we just count the number of carbon atoms in their chain. Usually there's no branch or anything, it's just one long chain. And then we go, after finding out how many carbon atoms that chain has, we go to our table of the stem names. We know that in this case we're making an example of pentane. It had 5 carbon atoms, therefore the stem name will be pent. And then since it's an alkane, the suffix will always be ane. Therefore the resulting name for that organic compound is pentane, right? So that's one thing. And then we said no prefix here for straight chain alkanes or simple alkanes. Right. So we would only have, let me take this. So we'd only have the stem and the suffix. Right, so what would the structural formula of pentane look like? It would have 7 carbon atoms. So it would be 1, 2, 3, 4, 5, 6, 7. Right, so when we say it's a straight chain, this is what we mean. See, it's just a chain of carbon atoms bonded to one another, and of course they are also bonded to hydrogen atoms. So now we can add our hydrogen atoms. Of course it won't be a perfect diagram, but as long as it has the accurate number of bonds, carbon atoms and hydrogen atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then finally our other hydrogen atom. So this is what a structural formula for pentane would look like. All right, and then obviously if you have a fewer number of carbon atoms, it would look like that. So for methane, for instance, it would have 1 and then just hydrogen atoms. Okay, this would be methane. For ethane, remember it has 2 carbon atoms, 2, and then you have ethane. For ethane, you'll have a small chain, which is 1, 2 carbon atoms. Then you have the remaining being hydrogen atoms, 1, 2, 3, 4, 5, 6. So in the structural formula and the general formula, you will find the same number of structural formula and molecular formula. You'll find the same number of carbon and hydrogen atoms. If you remember, our general formula says Cn H2n plus 2. So we have 2 carbon atoms, so we have C2. How many hydrogen atoms will we need? 2 times 2 plus 2, that is 6. So we can put 6 here. So if we come and count here, we'll find that 1, 2, 3, 4, 5, 6. There's exactly 6 hydrogen atoms. So that's why sometimes you don't need to, when you don't know the structural formula but you know how many carbon atoms there are there, you can always find the molecular formula of that particular alkane. All right, so that's one thing you need to note. So this would be our structural formula for pentane. Okay. This is pentane. Structural formula. Okay, so that's what it would look like. That's what it would look like. This would be methane. This would be ethane. We made examples of these earlier on, but we were not really concerned with IUPAC naming. But you should recognize these two, methane and ethane, from when we were still introducing this topic. All right, so this is what it would look like. And then you can of course also draw the condensed structural formula for this pentane, or for methane, ethane, and for any other organic compound for that matter. Right, so for this pentane, for instance, you would have something like the condensed structural formula. Remember, if you forgot what it is, you can go back to the intro, but you just come and you count how many carbon atoms are attached to each, how many hydrogen atoms are attached to each carbon atom. So you start from the first carbon atom on the chain to the last one. You write the carbon atom and you write the number of hydrogen atoms in it. So let's start with that first one. It will be C, and then how many hydrogen atoms do we have? 3, so it's CH3. And then we come to the next one, C again. How many hydrogen atoms? 2, so it's H2. So we are done with that. We are done with that. We come to the third one. It's CH2 again. I'm sure you can see. Fourth one, CH2. In fact, let's go take this to another page. All right. So we said this is the pentane structural formula. Now, the condensed structural formula would be we said C, we've already had H3, we're done with that one. We come to the second carbon atom, it has 2 hydrogen atoms. We come to the third one, it also has 2. So we're done with the first 3. We come to the fourth one, it also has 2 hydrogen atoms. The fifth one, it also has 2, CH2. Sixth also has 2, CH2. 7, that one has 3. So the first and last carbon atoms have 3 hydrogen atoms attached to them or bonded to them, covalently bonded to be specific to them. All right, so this is how the condensed structural formula would look like. Or sometimes you separate it using a bond like this. So it will be CH3, CH2, 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 CH2. These were 1, 2, 3, 4, 5, 1, 2, 3, 4, CH2, and then lastly CH3. Okay, so if you notice, this thing keeps repeating. This thing keeps repeating. It keeps repeating, even on the structural formula, right? So what they usually do, especially for organic compounds or alkanes in this context that have more than 10 of these carbon atoms in their chain, they would write the condensed structural formula in this manner. You would say C, let's write the structural formula, because usually it's used for the structural formula C, because we know that the first and last carbon atom will be attached to 3 carbon atoms, right? What repeats is in between these two, right? Which is CH, C and then H, like that. This is what repeats, right? And then this one will always be there, just 3. It won't repeat. It will be at the start and at the end. So the CH3s will be at the start and at the end of the entire carbon chain. And then in between these two, they are repeating CH2, 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 CH2 until the end of the structural formula, right? So what they do is they take this, or we take this, because it's us doing this now. We put brackets here. Of course, when we are doing it, you don't have to change color. I'm just doing it to show you that it's repeating. But in an exam, you wouldn't really have to change color. Right, we put them in brackets like that, and then we write M, right? So this M, of course, you would write a number, which will be how many times is this CH repeating, right? In this case, M would be equals to 1, 2, 3, 4, 5. 5. So it would be 5 here, right? So this is another way of writing. It's called an abbreviated structural formula, right? In fact, I was supposed to write it here. So we are saying right, so that CH, or this particular, this part, it keeps getting repeated over and over for about 5 times. Okay, so we can do what we call an abbreviated structural formula. We write the first C, which is the first carbon, and the last carbon, and then everything in between, because it's usually always the C or the carbon with 2 hydrogen atoms, and then it keeps repeating. We write those in brackets, and then this number will tell us how many times that will repeat, right? So this is called the condensed structural formula, right? So in its usual form, you would say, so in its usual form, you would let's say CH, like this. In fact, I should have taken that. Put it here. Right, and then you would put the M here, where this M is an integer, right? So now in our case, that M would be equals to 5 in the case of pentane, right? Because that CH2, which is this CH2, it repeats 5 times in between the CH3s, which is between the first carbon atom and the last carbon atom. So that's why we represent it like that. So yes, we call this the abbreviated structural formula. There's also an abbreviated condensed structural formula. So I'll show you just now what it looks like. It's just us saying we don't like tedious work, so we summarize the thing. So for a condensed structural formula, what we normally say is, okay, so this would be our example for that M will be 5. We'll call this an abbreviated structural formula for pentane. Okay, so that's the abbreviated structural formula for pentane, right? What about the abbreviated condensed structural formula for pentane and the actual condensed abbreviated structural formula in general, right? So let me remove this. This is all. Either you can choose to write it like that or like that. So there are two ways to write the structural formula. And remember, if you want to put something as a branch, you either put it in brackets or you introduce a branch here. So you would have something like this there. But we'll learn more about this when we start naming the not straight alkanes, or the not so simple alkanes, or the branched alkanes to be more precise. Because remember, we started with these ones, the straight chain alkanes, which are the simple ones. And then when we start doing the branched ones, you'll start seeing condensed structural formula or formulae of this nature. You maybe find CH3 there and so on and so forth, right? So yeah, so now for the condensed structural formula, the abbreviated version of this thing, pentane hydrocarbon, you would say CH3, right? And then you put that CH2, which is what's repeating, right, in brackets, and then you tell us how many times is it repeating. So you would have M here. Remember, M is the same thing as here, right? You went to the first carbon, you found that it has 3 hydrogen atoms attached to it. You wrote it here. You saw that there was this in brackets, the CH2 group, or the C attached to 2 either hydrogen atoms and 2 other carbon atoms, and you put it in brackets. And then there's the M, which will tell us how many times is that CH2 repeating in between the CH3s. Okay, and then you come back and put your CH3 again here. All right, so this is the condensed, the abbreviated condensed structural formula, or the abbreviated condensed formula. All right, and then now we will also do what it looks like for pentane, which is our example in this case. Okay, so we said that M since is equal to 5, since that CH repeats 5 times. So it repeats 5 times in between the CH3s. Between the first CH3 and last CH3. So that's what the condensed formula, or the abbreviated condensed structural formula would look like for pentane. And then the same reason why M is 5 here is the same reason why M was 5 for the abbreviated structural formula. All right, so that's that. Okay, remember that. This is for pentane. All right, now that's what we have for the straight chain alkanes. So if we go to heptane, hexane, octane, nonane, and decane, we will do the same thing. We'll keep adding another carbon atom, another carbon atom, another carbon atom, and so on and so forth until the chain has 10 carbon atoms in it, right? And then we will also count how many times is this CH2 repeating in between the first CH3 and the last CH3, right? So most of the times you will find that you don't necessarily need to write the abbreviated structural formula, but it is very helpful to actually know it, okay, just to understand where it comes from. Okay, so that's how the concept works. Now let's get into branched alkanes and how to name these. So when we're naming branched alkanes, we usually follow a series of steps, and that's what we will get to see now. All right, so now branches can either be called branches, right, substituents, and they're also called alkyl groups. So typically we use alkyl groups more, the word alkyl groups more than substituents or branches, right? But use whichever one feels comfortable to you. But you must know that if you were perhaps facing a question that is asking you for an alkyl group, you must know they're talking about a branch or a branch. Or if you are facing a question asking you about a substituent, it's either they're talking about a branch or a different element or different atom to where the hydrogen atom would be attached, right? I'll write all of these things down, so don't worry. But as an example, let's take our previous example of pentane, right? This was a straight chain hydrocarbon, right? So we take pentane. Now when we talk about branched alkanes, what you would find is where there's a hydrogen here, you might find that the way this structural formula is such that instead of having hydrogen there, we substitute it with a carbon atom, and in turn that carbon atom is bonded to either hydrogen atoms like this, right? Or maybe it can be such that, let's say, let me make it a bit longer, it's bonded to carbon here, another carbon there, and then we have our hydrogen atoms like this, right? So what you would notice there is, yes, there will be the long chain, which would be this would be the long chain, right? This would be the long carbon chain, the straight carbon chain. And then if you check on this chain, we have another branch, which is those two carbon atoms attached to those 5 hydrogen atoms, right? So that's what we would call a branch or an alkyl group or a substituent. The reason we call it a substituent is, if you remember, before there was this branch here or this branch, there was actually hydrogen here. There was a hydrogen atom that was attached here on this heptane. We're dealing with on this pentane chain, right? So there was one hydrogen that was attached there, but in this branched alkane, now instead of having hydrogen there, there's actually what we would call an alkyl group. So it doesn't, a long chain doesn't always have to be straight, it just has to be continuous. Okay, so what that means is, if you check, our long chain in this case is 1, 2, 3, 4, 5 until 7 carbon atoms, but we can also have another continuous chain there. Let's use, if I remove this, another continuous chain. If we start counting here, we come there, that's another continuous chain. In fact, it has 1, 2, 3, 4, 5, 6, 7, 8 carbon atoms, right? So that's another continuous chain. Okay, so we can take that as our main chain, or we can use the straight one as our main chain. We'll get to learn how to pick which one is which, okay? But for the main purpose of this example, I was just showing you how a branch or a branch would look like. Okay, so it would have a long chain. So if you check, even in our current long chain, which is a bit different from the first one, we still have a branch here. We still have a branch here, which is this one, right? It's outside the main chain, right? So when we find the carbon chain, it has to be long. No, it has to be continuous, which means if I start from this carbon atom and I keep joining, right, I have to continue joining all of them until I reach the end, right? As soon as I see something that's deviating from that path, then I know that's my branch or that is my substituent. Okay, so that's usually how it works. It works like so. It means now there's a number of chains that you can take out from this. So there's another chain that we can still take out from this organic compound, which would be, remember I started with the straight one. Another chain would be this one. If I go here and I join here, and then it ends there, right? Okay, that's also a chain, because it's a continuous chain of carbon atoms, right? The straight one is also a chain. The one where I start from here and I end up there is also a straight chain. So there's about 3 chains that have it's not a straight chain, it's a continuous chain. So there's about 3 continuous chains that I've found here. One of those chains was a straight one. So let's catch them again. Let's do them again. This point is very important. Okay, we have 1, which is this one, chain 1, right? And then I'll try to change the color, hopefully it works. We have chain 2, which I can start anywhere really. I can start from here and go all the way there, and then it continues and ends there. That's chain 2. And then we have chain 3 again. Chain 3 starts from this carbon atom. Can use a different color as well, doesn't matter, red. From this carbon atom goes to this one, there, and then there. Okay, that's chain 3, right? But the longest one, if we check, it's this one. The longest chain that we were able to find in these 3 chains was that one. Okay, and then the second longest is this one, the straight one, right? So depending on the chain that you identify, you will also get to see a certain alkyl group or a certain branch, right? So one thing is we have to also name these branches. So the way we name them is it depends on how many carbon atoms that they have. Okay, right. So let's take this away. We are saying branches are also called alkyl groups or substituents. Right, so like I said, branches are also called substituents or alkyl groups. So typically we will have a longer carbon chain, and then in that carbon chain, that longer one, we would call it a parent chain or the main chain. So most people prefer using main because it's easy to remember. And then there will be shorter chains which will be on this main chain, right? Those ones are called then the branches or side chains, right, or substituents. And then we also call them alkyl groups, right? So typically I prefer using alkyl groups because it's most commonly used. Okay, so that's what happens, and depending on the number of carbon atoms in this chain, we name them accordingly, the alkyl groups, right? So okay, alkyl group is named according to how many carbon atoms it has. So how does the naming convention look like? So it's the same as when we were giving stem names on the number of carbon atoms, but now the only difference is they are no longer incomplete. Like with a stem name, basically it would need a suffix to complete it, right? So we would have meth, and then the suffix would come from the homologous series. In our example, from what we've covered now, it would come from alkanes, which is A and E, right? And then if it has one carbon atom, that particular organic compound would be methane, and so on. But with alkyl groups, we still use the number of atoms in that alkyl group, but instead of saying meth, we will say methyl or ethyl or propyl, and so on and so forth. So let me come here and show you. So check our table here. So in this table we have number of carbon atoms from 1 to 10, same as the table where we were giving names for the stem names, right? So if that particular chain branch has 1 carbon atom, we would call that a methyl substituent or a methyl alkyl group or a methyl branch, right? If it has 2, it would be ethyl. If it has 3, propyl, and so on and so forth until decyl. So typically for grade 12, we normally won't find these from butyl up until decyl. These are not really most commonly found in grade 12. You won't really find these in grade 12. In fact, I should make it red. So if you check the ones that are in that red box, you won't really find them that much in grade 12 questions and exams and tests, right? You will mostly find methyl or ethyl. In some instances, you might find propyl. Okay, so yeah, because the chain gets way too long for you to be able to find anything from butyl down to decyl. All right, so that's how the alkyl groups work. So let's take an example of our pentane. So in pentane, let's say we had a chain, right? For the sake of example, say this is our hydrocarbon, right? So don't worry now about the naming and everything. We will get to it in a minute. We are just illustrating a point. And then there's a branch here. Right? This would be our example. This branch would be an ethyl branch. So what would happen is you would get what we call the parent chain, which is this one. Okay, that doesn't look nice, right? We would call this one our parent chain, or let's call it main chain. It's easier to remember. Some people call it the parent chain, okay? And then in this main chain, you see that there's a branch away from it, or where there was supposed to be an H atom, we now have an alkyl group, which is CH3 in this case. Right, that's what we would call our alkyl group. So since it has one C atom or carbon atom, it will therefore be methyl group. So that's how you would identify, as an example, these types of substituents or branches. Okay, so that's one thing about branches when it comes to naming branched chain alkanes. Okay, all right, so another thing that you must understand is, you see these alkyl groups or these branches, they can repeat. It doesn't have to be one branch. In an event where they do repeat, it might be the same alkyl group repeating, which means, let's say maybe down the line you find that there's another branch here. It's also CH3, right? Or you might find that it's not CH3, it's just C like this. It has two carbon atoms. Okay, so they might repeat, and depending on whether or not we are repeating the same alkyl group, if we are repeating the same alkyl group, there are names that we must use. So there's a certain way of naming them. So for repeated alkyl groups, we start using the normal Greek prefixes that we usually use in physics, maths, and so on. So for instance, if there's one of that thing, it would be mono. If there are two, it's di. 3, tri. 4 is tetra. Right, so that's what we typically use. Then we would say okay. In fact, let's actually write it here. If the same alkyl group repeats, we use Greek prefixes mono, di, tri, and tetra. 1 for mono, 2 for di. 2 we use di, 3 we use tetra, and then 4. Okay, let's do that again. 1 we use mono, 2 we use di, 3 we use tetra, and then 4 we use tetra. All right, so let me write it down. If same alkyl group is repeated, we use Greek prefixes. Of course, it sounds weird to say it's repeated and then there's only one of it and then we say mono. It doesn't necessarily work like that. So we would typically use di, tri, and tetra. All right, so we would have one. Remember, this is just a reminder that one means mono. Two, we use di, right? Three, we use tri. I don't know why I kept saying tetra, so I suppose it's better for me to write it. And then four, we use tetra. All right, so typically you would use these three. All right, but the most common one is tri. So di and tri are the most common ones, but that's what happens when an alkyl group is repeated. So now let's lay out the rules and start naming these branched chain alkanes. Okay, so we are officially starting with the rules on how to name these branched chain alkanes, right? So the first rule that we follow is, firstly, we must find the longest continuous chain of carbon atoms in the molecule. So what we'll do is, there are about 6, if not 7 of these rules. So for each rule, I'll just give an example of what it would look like to apply that rule, okay? Because the list is a bit too long to fit in one page. All right, so also it makes more practical sense if I cover an example for each rule, then the knowledge will better solidify. Now let's take this example, right, this one, to illustrate this rule. So this rule says we find the longest continuous chain of carbon atoms in the molecule. All right, so our molecule here, we'll take this as it is. This is our example. All right, so in our example, remember, we found our longest chain to be the one labeled, it's labeled as the main chain. So it's also called the parent chain, main chain or parent chain, remember. It's also called a parent chain. All right, so that's our longest chain, right? So once we've found this longest chain, it will determine our base name. What do we mean by that? It means that we will use the long chain and count how many carbon atoms it has, and then we will know what the stem of our hydrocarbon will be. In this case, we're dealing with a hydrocarbon. In another case, it won't necessarily be a hydrocarbon. So we will know what is the base name or what is the stem of our organic compound. So since main chain has 1, 2, 3, 4, 5, 6, 7 carbon atoms, right? It means now this main chain will have a stem name of hept, right? So, and then since it's an alkane, the suffix will be A and E. All right, remember that. Our suffix is A and E. So if you remember from a basic or from a straight chain alkane, we would usually have a base name of, we take the stem plus the suffix and we get, this will be our base name. heptane. So the name of our longest carbon chain is heptane, right? That's where we start. What's our longest carbon chain, and therefore what is its base name? So its base name is made up of the stem plus the suffix, similar to how you would name a simple straight chain alkane, like what we were doing. Where is it? Here. So here would say, how many atoms does the straight chain alkane have? How many carbon atoms? If it has 3, we would call it propane. If it has 4, butane, and so on. So now, instead of naming the whole organic compound in this simplistic manner, what we are doing is we are breaking down the name. So we first name the longest chain, which we name the longest chain the same way we would name a straight chain alkane. So since this long chain, we've identified it has about 7 carbon atoms, we will take a stem that corresponds to that 7 carbon atoms, and then the suffix of the organic compound that we're dealing with, which is A and E in this case, to form the base name, right, for the alkane. So it will be heptane for this chain. Now, another thing that we must note is the longest chain is not always straight. So what example would that look like? Let's change this. All right, so if we check our other example here to show that the longest chain is not always straight, okay? So check this compound of ours here. So the name of it is not really important for now, because just to illustrate the example that the longest chain is not always straight. It's not always as straightforward. So if we check our straight chain, the continuous straight chain runs from here, and this is the straight continuous chain, okay? In fact, so right, that's our straight chain, but is it the longest? Right, let's check. It has 1 2 3 4 5 6 7 8 carbon atoms, right? That's our first continuous chain that we could determine. Okay, so if we check another continuous chain, we find that we have, let's see, this one. That's another continuous chain that we can determine there. Because remember, they won't always be straight. Continuous chains don't always have to be straight. So we found this zigzag one. It has 1 2 3 4 5 carbon atoms, okay? Then there's another one. If you start, let's say you start here, 1 2 3 4 5 6 7 8. That's another one. So this one is the same one, has the same number of carbon atoms as the straight one, okay? As the straight carbon chain. Okay, that's fine. So the longest carbon chain we have identified so far has 8 carbon atoms. What about this one, where we start? We can even start here and check 1 2 3 4 5 6 7 8. This one also has 8, so it's not really the longest continuous chain. It's probably the longest because we've identified 3 of them that have 8, right? So let's find from here again, 1 2 3 4 5 6 7 8. Okay, so if you check, the highest number that we have seen is 8, and there's about 3 chains that we can identify, 3 continuous chains that we can identify that have 8 carbon atoms in them, right? So obviously the one that is straight would take preference, but it's not always the case. So let's say, for instance, you had something like this. So the straight chain would take preference if we identify long chains and they happen to be of the same length. The one that has a straight continuous chain would take preference when we start naming them, the compound. All right, so let's count now. So if we add something like this, what will happen is, now if you check, let's say we start counting from this carbon atom, 2 3 4 5 6 7 8 and 9. Okay, now we have a carbon atom or a continuous carbon atom chain that has 9 of these carbon atoms. Okay, now if we check all the other carbon chains that we can identify here, starting with this one has 8. Okay, let's say we find another one, perhaps from, you don't stop until you reach the last carbon atom in that chain. If we find this one, we say this one is 5. Okay, if we check this one as well, this one would have 1 2 3 4 5 6 7 8 9. Okay, so there are now 2 carbon chains that have 9 carbon atoms in them, and both of them are not straight. They are like that. Call it a zigzag if you want, but they are not straight, and they happen to be longer than this straight continuous chain. Straight continuous chain has 1 2 3 4 5 6 7 8. The ones that are not straight, like this one, 1 2 3 4 5 6 7 8 9. So that's one thing to be aware of. Okay, the longest continuous chain will not always be a straight one. Okay, so I will pick this as my longest continuous chain for now. Okay, that's our long chain. I think we should use the same color. Right, so that's our longest continuous chain, and then just to allow space for information, we'll put it here. Right, I can then point you to it. It's a bit tedious, but that's our longest continuous chain. Now if we check our longest continuous chain, it would be the main or parent chain, right? You can call it the main chain. And then it has 9 carbon atoms. What does that mean? It means the name of this chain, which we call the base name, would be, what is an alkane that has 9? And no name, we'll use this one to name our parent chain. So our parent chain's name would be non-name, right? The stem would be non, the suffix, which we are still dealing with alkanes, will be ane. And remember, the base name or the name of the longest chain is simply the stem plus the suffix, which will give us, let's call it base name, it gives us nonane. So just to clarify, when I say base name, I mean the name of the longest continuous carbon chain. Okay, so that's what I mean by base name. Don't want you to be confused here, okay? So when we say it's not always straight, that's what we mean. All right. So in this case, now that we've identified our continuous chain or the long chain, we can then find our alkyl groups, which is anything outside this longest chain. So this is my first alkyl group. This one, right? If you check, it has 2 carbon atoms. Right, it has 2 carbon atoms. Okay, my information might not fit there. We'll try. So since it has 2 carbon atoms, it means it should be a ethyl group. Remember, if an alkyl group has 2 carbon atoms, it's an ethyl. Okay, why is it an alkyl group? Because it's a branch. It's outside the longest continuous carbon chain. Anything outside the longest continuous carbon chain is what we call an alkyl group in the case of hydrocarbons or alkanes in this example. Okay, so that's what happens. And then our second one would be this one. It's outside the longest chain, so it has to be an alkyl group. Okay, so this one would be what we call methyl. Right, so that's how you would identify the alkyl groups, which are the branches, and also the longest continuous carbon chain. Longest continuous, let me finish it off here. Carbon chain. All right, so it's the main chain or the parent chain, depends on which one you prefer. All right, so then now you would combine all of these to make a name. Right, so this then takes us to rule number 2. We will continue using the same example so that you don't get confused. Okay, now to rule number 2, we say, all right, rule number 2, we now number the carbon atoms in the main chain so that we give the alkyl group the lowest number. Let me show you what that looks like. So we come here, we have this, right? I'll just take it as it is. We will continue with this example, these 2 compounds, until until we finish these rules or steps on how to name alkanes. Okay, all right, let's take this as it is and bring it this side. So now we have this. We have the main chain, which happens to be the longest continuous chain. Continuous chain, and then yes. So now what we're saying is, on this chain, you must start numbering the carbon atoms. So basically what you're doing is you're saying, on my chain, this carbon atom is number 1, this one is number 2, this one is number 3. But when you are doing that, you must make sure that the side where you will start numbering from, because you can start from either side. You can either start from left going to right, or you can start from right going to the left. What that means is I could have started here and said 1, 2, 3, and so on. But I started to the left in this case. So how do you decide where to start? This is what this rule is saying. You decide based on where is the alkyl group located. So when you number, if you check, let's start numbering from the right, for instance. Okay. If we number from the right to the left, we'll use a different color. We will get 1, 2, 3, 4, 5. So what this means is the alkyl group is found on the 5th carbon from the left. Okay, then we continue 6 and then 7, right? Now what if we start numbering from the left now to the right? Okay, if we do that, we'll then have 1, 2, 3. Now, if we number from the left to the right, we find that the alkyl group is located on the 3rd carbon, okay, which is lower than when we are numbering from right to left. So let's finish. Then we have 4, 5, 6, and 7. So what we're saying is you number from the side that will give your alkyl group the lowest position number, right? So the lowest position, I will get it if I number from left going to the right. I get that my alkyl group will be number 3, will be on position 3, or will be on the 3rd carbon atom from left. However, if I do it the other way around and I start numbering from the right, then I will find that my alkyl group is in position 5. So I choose when it's in position 3. That's what I want, because that's the lowest position. So I choose numbering from left to right. So I will write it here. for these last set of rules, I will just put all of them here, the remaining ones, because they are dependent on the type of organic compound we're dealing with, some of them. For instance, if you check, it says we must now name the alkyl group and then write the final name of the compound. But if we have two or more identical alkyl groups, so that's condition number 1, and none of our 2 examples have identical alkyl groups, okay, so that rule won't apply. And then number 5, it says if 2 different alkyl groups are present, so number 5 will apply but number 4 won't. And then lastly, number 6 will apply because we are writing now the name as a single word. All right, so let's take our compound and put it here. Okay, copied everything. All right. We take our compound, we put it there. Now we go to rule number 3. It says name the alkyl group and write down the name of the compound. Okay, so let's come in. Our alkyl group is the methyl group, and it is on carbon number 3. So this will be 3-methyl. So the rule says, which is rule number it's actually the final rule, whenever we write a number and then a name, we separate the two with a dash, right? So since it's on the 3rd carbon atoms, we'll write the number of its position along the carbon chain, which is carbon number 3, and then we write that name of that alkyl group. So it's our methyl group, this one, methyl. Okay, so that's another rule. Whenever you now start writing the final name, numbers, you separate numbers from each other using commas. For instance, 3, 3. And then you separate numbers from alphabets using dashes. For instance, methyl in my case. Okay, that's one thing you must understand. So now what happens is, in this case, we don't have multiple alkyl groups, so we won't need to separate numbers with commas like this, because we usually do that when there are multiple alkyl groups, but you will see in the other examples that we have in store. All right, so this would be 3-methyl. That's the first part of the name, okay, which is our prefix. If you remember, we didn't have prefixes when we were dealing with straight chain alkanes, because now we're doing branched chain alkanes, right? So this will be 3-methyl, and then we continue. We are told that if 2 different alkyl groups are present, we list them in alphabetical order within the final name. So here we only have 1, so it's fine. And then if we only have 1, we write that 1, and then now we write the base name to finish off this name. So there's nothing else we can add here, so we can just finish it off using that base name. So remember, our base name was, what's the name of the longest carbon chain? So since it's 1, 2, 3, 4, 5, 6, 7 carbon atoms, that's heptane. That's how you would do it. Okay, so it's 3-methyl heptane. That's the name of this organic compound. So you don't separate the suffix, stem, and the prefix, because they are all letters, but you separate numbers to numbers and then numbers to letters. I repeat again, with numbers to numbers, you use commas, like when I said 3, 3. Whereas with numbers to letters, you separate those using a dash, like the one that you are seeing here. Okay, so that's what this compound will come out to be. So that's our example 1. Now let's get our other example. we take this one again, and we bring it this side. All right, here we now have two alkyl groups. Okay, so what happens when you have two alkyl groups? You must start numbering them, and then of course we had decided to that we'll be numbering this from left to right so that we give the ethyl group the lowest number. The reason we decided to give ethyl group the lowest number is because alphabetically E comes first before M. Right, this is one of the few instances where you have to use alphabetic order. Okay, so this is example 1. So now what happens is here we will start numbering them as well. Using rule number 3, we'll name the alkyl groups. There's 3 of them. So this one, since it's number 3, we will have 3 ethyl, right? We haven't started combining anything yet. And then we will have another one, which is number 7 methyl. So I have 2 of these alkyl groups, and I'm naming them according to where they are along the long continuous carbon chain. Okay, now that I have those 2, I must start combining them to form the full name now. So how do I go about it? In the full name, I make sure that ethyl comes first and then methyl. Right, so if you check our rules here, since there are 2 different alkyl groups here, we list the different branches in alphabetical order within the final name, as I've already specified. And then there's something else. If, let's say, the ethyl group was repeated twice, I would have said here, maybe it could be in 7, both of it. For instance, if it was repeated twice, you would find that it's in the same carbon atom. So I would say 7 and again 7 within the same carbon atom. And since there's 2 of them, this will be a dimethyl. That's when we would use the Greek prefixes. Right, but now, since it's only 1, so we'll just use methyl. That's what the rule is saying. But don't worry, more examples are coming. All right, so what it then boils down to is now we can combine these because we have the base name. Remember, our base name is nonane, because we have 9 of the carbon atoms on that long continuous carbon chain. So now we can start combining them. So it means our full name now will be 3 ethyl, right? Remember what we said, you separate numbers and letters using a dash. So now I must add my other alkyl group and its position. So I put a dash because I will add it here, 7 methyl. Then I add my base name after, nonane. That's how you do it. So that's how you name these things. So these 2, remember, we carried them from our first rule. So now let's try to see when we have other compounds, right? And then we'll just follow these rules again and again and again, right? So let's check other examples. All right, so we will be naming the following alkanes. All right, so we'll be using the rules we've been using since. So first of all, let's start with this one. We want to identify the longest continuous carbon chain. All right, so In this case, some will be tempted to say, okay, that's my chain, right? And then therefore, this is my branch 1 and that's my branch 2. So that's technically not true, right? So it's not correct. So whenever you are identifying the longest chain, just remember that you will never have the chains or the substituents or the alkyl groups being located in the first and the last carbon atom within the main chain. It's not possible. Okay, so always know that as soon as you have substituent groups or alkyl groups or these branches in the first or in the last carbon chain, just know that that is not true, right? So this means that's not our chain. Our chain actually runs from 1, 2, 3, 4. That's it. So that's our longest chain. And if we check, it does not have any alkyl groups. So that means we can take this as a simple alkane, a simple straight chain alkane, and name it accordingly. So now, how many carbon atoms does it have? Find that it has 1, 2, 3, 4, 5 carbon atoms. It has 0 alkyl groups. So this is just a simple or a basic alkane. So therefore, stem name would be, we said 5 is what? Let's go to our table. Stem name, no, not this one. 5 is pent. So let's go back. Pent. And then our suffix, since this is an alkane, we can check as well the carbon to carbon bonds are single bonds, carbon to hydrogen bonds are single bonds as well. So everything here is a single bond. So it's an alkane, A and E. And we can even check the general formula. You find that it's actually CnH2n plus 2. Alright, so this is the information that we have. Now, we then understand that since it has no alkyl groups, it's a simple in fact, let me write it here. This would be a simple pentane. Okay, so of course pentane can also be written like this. Right? In fact, these organic compounds, they are not spread out like this. They come as zigzags. You might find that the pentane that we're given in this problem is the accurate one compared to the one that I'm actually drawing now. So they are not as straight like this. They come in zigzags in their actual nature or in their actual form. Right, so I left this space so that I can show you that it's not allowed to say that this is our longest chain. It's not allowed, okay? You can't do that. Because then you would have this being your alkyl group. In fact, let's use blue. and that one is open your alkyl group. So this is incorrect. Okay. This is incorrect, and there's a set guy there. The reason for that is, remember I said you cannot have an alkyl group attached to the first or the last carbon atom in the main chain. So that's our reason, right? I've stated our reason there. So yes, so now this means this one, that's our main chain. That's it. Okay, so that's one thing you must understand here. So let's move on to this example now. Example 2, we have this guy. So let us identify our longest chain. Of course, it's a matter of trial and error. You don't just, unless you've practiced long enough. Once you've practiced long enough, you can just look at it and you will see the longest chain, okay? But just be comfortable with trying and failing and trying and testing out different chains. All right, so let's start with this one. There's this chain. This is clearly not the longest chain. It gives me 3 carbon atoms, and I can see there's a lot more left. Then I check the straight one. The straight one gives me 1, 2, 3, 4, 5, 6 carbon atoms. Okay. Then now let me check this one. 1, 2, 3, 4, 5, 6 as well. Okay. So I have 2 chains that are both giving me 6 carbon atoms. Then now I have this one. 1, 2, 3, 4, 5, 6 as well. So I have 3 chains that are giving me 6 carbon atoms. What do? I choose the longest chain. I mean the straight chain. It takes preference. This one. Because I value convenience. So this is 1, 2, 3, 4, 5, 6. It will be even easier to number my alkyl groups here. Okay. But please note that it doesn't stop you from choosing this chain. Okay, you are still correct for choosing that chain. Okay, but by default, because I like convenience, I'll choose the straight one. Okay, because it's easier to deal with. So we will name both of them and you will see. So let's start. What we see here is, let's start naming from the side that will give us the lowest number of the alkyl group. So we can see that if we start numbering from right to left, this is an alkyl group. Of course, let's just note that that's alkyl group number 1. And then that's alkyl group number 2. Okay, so we have these 2 alkyl groups now. One is methyl, the other one is ethyl. So we have methyl here, and then we have ethyl there. Okay, now let us start numbering. We will number such that it gives ethyl the preference, because ethyl comes first alphabetically. E comes before M. So if I start numbering from left to right, I will get 1, 2, 3, 4, 5, 6. My ethyl is number 4. Okay, now what if I number from right to left? I'll get 1, 2, 3, 4, 5, 6. So my ethyl will be number 3 in this case. So I choose to number from right to left, the green one. Sorry if you can't see color, but yeah, just note that I'm numbering from right to left because I get the smallest number for the ethyl group. Why am I choosing to get the smallest number for the ethyl group? Because it gets alphabetical preference in this case, since E comes before M. Right, so now we can start doing our things. We see that we have, okay, six carbon atoms on parent chain. Okay, and then we also see that we have 2 alkyl groups, which is ethyl and methyl. All right, that's something we see as well. And then another thing, we number right, so we are numbering from right to left so that we can give ethyl the lower number in the carbon chain, the lower position number in the carbon chain. Right, so now that we've done that, it means we get ethyl being 3 ethyl, right, and methyl will be 5 methyl. Where did I get those? I took them from here. We are at 3 and 5. Okay, 3 and 5. I hope you can see that. All right, so therefore what we end up doing is, therefore our name will be three ethyl. We add our other alkyl group, 5 methyl, and then we add our base name. Oh, I forgot to mention our base name. Since it has 6 carbon atoms, our base name let's put it here, main chain. Our main chain is 6, so it has to be hexane. Right, so then we can finish off our name and add hexane there, hexane. Right, so that's how you would complete a name for a compound like this one. So we have another example. But before we do that, copy, I wanted to show you that you can still do this even if you chose this branch. 1, 2, 3, 4, 5, 6, right? Even if you chose this branch, it's okay, you can do it. Your number, you get your alkyl groups there, it's still fine. That's alkyl group number 1, it's on the outside of the main chain. That's alkyl group number 2. Excuse me. So how do we name this one? So with this one, if we had chosen this chain, you would find that if I number from up to down, for instance, I'll get that this is 1, 2, 3, 4, 5, and 6. Then if I number the other way around from down to up, I get this 1, 2, 3, 4, 5, and 6. So since I want to give ethyl the preference, this will be 3 ethyl so that it gets the lower number, right? And then methyl then would have to be 5 methyl. If you check, coincidentally, I'm getting the same. I'll pretty much get the same name. Okay, so it becomes a matter of where you are looking at it from. But as long as you selected the longest possible continuous carbon chain, you will be fine. So here you'd still get 3 ethyl, right? 5 methyl, and then hexane, because there's 6 of them, hex. All right, just to double check, if there's 6, yes, it's hexyl. So this one is hexane because I'm using the stem and the suffix for the main chain. Okay, now we are given a different scenario now. So if you remember, this is just a condensed structural formula. It's nothing different, it's still the same thing. All right, now how does it work? So we have this. Let's identify the longest chain. So remember, these lines, they represent, in fact, let me make them darker. They represent our bonds. All these lines. Don't let them scare you. All right, so let's mark them. If I start with a simple straight one, I'll get 1, 2, 3, 4, 5, 6. All right, it has 6 carbon atoms. Okay. Or I can do it like this: 1, 2, 3, 4, 5, 6. Okay, that still has 6. So the two long chains that I've identified so far, both have 6. Okay, what about if I come now and say 1, 2, 3, 4, 5, 6? I get the same thing. Okay, so what is this telling me? It tells me that I can choose whichever one of these chains. So, you know me, I will always go for the simplest option that I have. So I'll just choose the straight one, which is this one. So if you are given something like this and you see that you are struggling because you can only see it when it's in structural formula form, it's okay, you can sketch it to be a structural formula. So in this case, it would look like, you'll have your carbon atoms there. See? So that's 1, 2, 3, 4, 5, 6. Okay, let's first sketch those ones. Okay, now that we have those ones, on the third one we can get a CH2. But then this CH2 is, in fact, we can put it like this if we want. It's also attached to another C, and then that C has an H there, but this C is also attached to a CH3 here, and then it's also attached to another CH3 there. I'm just following the condensed structural formula. It's the same thing. You're copying it, but now you are just expanding it. Okay, I think that's pretty much, it's a bit clustered, but it should give you the idea of what it looks like to take a condensed one and turn it into a structural formula. So this is what it would look like. So now you can pretty much trace whatever you want. So you can do 1 2 3 4 5 6, right? Or you can do what I did, 1 2 3 4 5 6. So now you have something like that. All right, so we will just do, there are about 2 ways to name this one. So we'll do both of them, and then yeah, so let's do this, move it there, and then we see this one. So we see that we have a main chain, and then we just have one branch or one alkyl group. So we go to this alkyl group, we count how many carbon atoms it has. In fact, we might have made a mistake here. We forgot to trace all our parts actually. So if we check this one, 1 2 3 4 5 6 7, okay, all of the other ones were 6. This is the only one that has 7. Let's see this one, 1 2 3 4 5 6 7 as well. Okay, I don't know how we made that blunder. 1 2 3 4 5 6 7. All right, so our longest path is actually 7. It's either we go that way or we go this way. Oops. 1 2 3 4 5 6 7. So we can use either one of these. Okay, so for now let me use this simple C looking one, 1 2 3 4 5 6 7. Okay, so always make sure to check all possible parts. Don't skip a step there. All right, so we have 7 carbon atoms there. So if we start counting, it means now we will get a branch here, right, and another one there. One is a methyl, one is an ethyl. So this is what an ethyl group, and this is a methyl group. All right, so now we will prioritize the ethyl when we count. So if I count from here and I say 1 2 3 4, in fact let me put it here, 4 5 6 7, my ethyl group becomes number 4. Okay, on the other hand, if I count from here, 1 2 3 4 5 6 7, either way my ethyl group will be number 4. All right, so what I'll do is, if you notice, whichever way we start numbering from here, the ethyl group is always in position 4. So it's fine, we don't have to prioritize it now in terms of the numbers. So let's check the methyl group. The methyl group, if I number from bottom to top, it's on number 2, but if I number from top to bottom, it's on number 6. So I will choose the one that gives me the lowest number for this one as well, which is from bottom to top, the red one. So I'll choose this system where I start numbering from here. 1, oh no. So my numbers will be this one and that one for my alkyl groups. So what that means is I will have, okay, in my parent chain, 6, what was it? 1, 2, 3, 4, 5, 6, 7, 7 carbon atoms in my main chain. Right, and then what else? We have 2 alkyl groups. I will list them as they are. We will get 4 ethyl, and then we have 2 methyl. And then what else we have? We have parent chain name. That's something else that we have. Will be heptane, because it's 7 carbon atoms. So heptane works. So now from here on, we can then start with our full name. Remember, we separate numbers and letters using dashes, but numbers and numbers using commas. So for now, there's no example that allowed us to separate numbers and numbers. Okay, so here we will have, therefore our name will be 4 ethyl, because remember we start by ethyl because it comes before M. E comes before M. And then 2 methyl, and then we put our parent chain name, which is heptane. That is our answer. All right, so what if we had numbered it what if we had marked it using this way? Seems like we'll still get the same thing, because we'll have 1, 2, 3, 4, 5, 6, 7. Yeah, you'd still get the same answer. You'll get that 2 methyl, because this is a methyl group, this one. And then 4, because if you check, we will get this guy being our alkyl group, and that guy being our other alkyl group. So if you check the positions, they are in the same positions as when we were using a different chain, which is this one here. All right, so you'd get the same answer. So I just wanted to add that we chose to number from up down going up, so that methyl gets the lowest number. All right, let's do this last one. So if we trace here, we have 3. If we trace here, we have 5. And then if we trace there, right, we have 1, 2, 3, 4, 5, 6, 7. Okay, if we do the long chain, we have 1, 2, 3, 4, 5, 6, 7 again. So I'll choose the long chain because I like convenience, right? Because convenience is my favorite thing. So let's choose that long chain. So we get that the parent chain has 7 C atoms. Let's call them C atoms. Right, heptane. This means it's a heptane parent chain. What else do we know? we can identify our alkyl groups. I see one here outside my branch, another one there, and then a last one there. As long as these are not attached to either the first or the last carbon atom in the longest continuous chain, okay, then we can call them alkyl groups. Otherwise they are disqualified. All right, so we have those, and then now we can start. So if we check, if I number from this side, from left to right, I will get 1, 2, 3, 4, 5, 6, and 7. All right, and then if I number from left to right, from right to left, I get 1, 2, 3, 4, 5, 6, and 7. So in this case, it doesn't matter whether I number from left to right or from right to left. I get the same positions for each of these alkyl groups. And since it's the same alkyl group repeating, it doesn't matter, right? So I'll just start numbering from left to right, okay? I see that I have alkyl groups in these 3 positions, okay? So let me just list them here. In position 2, I have 2 ethyl. Sorry, that's a mistake. It should be methyl because it's 1 carbon atom. I have 4 methyl again, 1 carbon atom. I have 6 methyl again. Remember what we said. If an alkyl group repeats and it's the same one, we must start using the Greek prefixes. We need a Greek prefix. Try, because there's 3 of them. All right, so I'll show you how to integrate this into the name now. So okay, we have the parent chain name, we have the alkyl group names and their positions along the long continuous carbon chain. Now we can start naming this thing. So we say 2, because it's the same group repeating, we will say I have position 2, comma, I have position 4, again another comma, and position 6. In all these positions along my long continuous carbon chain, you will find my methyl groups. How many of them are there? 3. I use trimethyl. Then now I put my parent chain name, which is heptane. Okay, that's it. Okay, so if you remember, once again, that would be our suffix. This would be our stem. And then this one, this whole thing would be our prefix. Okay, so that's how branched alkanes get their names. All right, so it's unlike the simple alkanes where you just get the stem and the suffix. With the branched alkanes, you will also get the prefix as well. All right, so this concludes the video, right? I'll catch you on the next one when we talk about alkenes.